Morning, everyone. Questions while we wait? Morning, everyone. Come on in. How are we doing? Any questions, anyone? Danielle is asking for an example of an inequality with different base pairs. Why don't we consider this, then we'll get to Jet's question. Wait. Which is square root of ln x over ln of square root of x equal to 3. Work those two things out. I'll be back in a moment. Yeah. All right, sorry about that. Let's try the first one though. What do I want to say? Let's ask the question, when are they equal? Are they equal? When is 3 to the x equal to 2 to the x squared? Right, that's going to be kind of a limiting point, if you will. And to work out the equality here, I would take ln of both sides, allowing us to bring the powers down. Bring everything to one side. Factor out an x. This is ln 3, sorry. And now we have a product equal to 0. And as you know, the only way that can happen is if one of the factors was 0. So either x is equal to 0 or x ln 2 minus ln 3 is equal to 0. And this occurs when x is ln 3 over ln 2. All right. So when x is one of those two things, you have equality, which means that we have to determine what happens outside of those. So we have to determine what happens in here or what happens in here or what happens well, I mean, I jumped the gun in saying that this was bigger than 0. It's not immediately clear, but you can work that out, right? And observe that, what's to observe? So, I mean, if we took a number in here and tested, if x is -1, if x is -1, 3 to the -1 is 1/3, and 2 to the -1 squared is 2. So 2 is bigger than 1/3. So in this interval, 3 to the x is going to be less than 2 to the x squared. Here, if you take a very large number, doesn't actually have to be too large. If you take x equal to 2, we're going to have 3 squared, which is 9, versus 2 to the 2 squared, which is 2 to the 4, which is 16. So in here, 3 to the x is going to be less than 2 to the x squared as well. It's only in here that you have the opposite inequality. And how are we going to convince ourselves of that? You could take any point in here and test. So, you know, if you have a calculator, you can work that out. Now you're thinking to yourself, well, what if I didn't have a calculator? What if this was an in-person exam? Well, if you give this a bit of thought, what's a number that is less than this one, but still bigger than 0? And I'm going to suggest, even though I don't know what this actually is without the use of a calculator, well, 1, it's probably, right? Because ln of 3 is bigger than ln of 2. Very nice, very nice. So 1 immediately. But what if this had been, what if it had been the opposite? Ln of 2 over ln of 3. Then it's something less than 1, and we don't know how far it is, how close to 0 it is. You could just say half of that. Half of it, if this is positive, half of it is still positive, and it's smaller than this, regardless of whatever that was. So very nice, but as pointed out, it's ln 3 over ln 2, so you could just use 1, or you could use half, and regardless, somebody suggested 1, and 1 is obvious, right? It's 3 versus 2, and this one is bigger, so 3 to the x is bigger than 2 to the x squared in this interval. Very nice. And then somebody was working this out. Similar, right? Let's bring this to the other side. And we get ln of x square root is 3 ln of square root of x. which is really 3 ln x to the 1/2, which is really 3 over 2 ln x. So we have ln of x, the square root of ln of x is equal to that. Now, as long as you do the same to both sides, equality is maintained. Square both sides. So if we square both sides, we get ln of x is 9 over 4 ln squared. Bring everything to one side. Oh, this is almost identical to a Weber question. Well, then let me stop here. No need for me to continue. In fact, I've probably done too much already. Then it's the same as before. Bring everything to one side, factor, and so on. You know what to do. Questions here? How are we doing? Anyone? Why does the x not get squared here? Well, I'm squaring the whole thing. So it's still, right? This is 3 over 2 ln x times 3 over 2 ln x. What was the final solution for the first question? You should write a final statement. The final statement was this union this. Well, look, I mean, you know, here's the thing. The point with web work is not to get the question right. It's to make sure that you understand the material. So there's really no point in me doing the question for you. You have to be able to do it yourself. You were stuck. I unstuck you now. Now you go ahead and finish it up. Questions? Last time we were doing inverse trig. Sophia's asking, why are we squaring both sides? Well, we would like to get rid of the square root. Matt is asking for e to the 2 to the ln squared of x is equal to x. Geez. Well, my first thought would be to take ln of both sides, leaving you with 2 to the ln squared x is equal to ln x. And if you replace, you get 2 to the y squared is equal to y. There's no solution to that. Right, let's not call it y, let's call it big X. right? And if you graph y equals 2x squared, what does that graph look like? It's going to kind of look like 2x uh, 4x bigger than 0, and since it's even, and then y equals x is this. So they don't intersect. All right, let's move on. Let's move on back to what we were doing last time, namely inverse trig functions. Let's do a few examples of that. We are asked to evaluate arctan of root 3. Right, so I mean, we don't know what that is. This is equivalent. Right, first of all, we don't know what that is, so let's give it a name. Let's call it theta. This is equivalent, if you take tangent of both sides, to asking the question, right, since tangent and arctan are inverse functions of each other, these just cancel out. And this is equivalent, so asking this question is equivalent to asking for what value of theta is tangent theta equal to root 3. And as Joanna has suggested, the answer is pi over 3, right? Because you know tangent is sine over cosine. And you know that sine of pi over 3 is root 3 over 2. You know that cosine of pi over 3 is 1/2. So tangent of pi over 3 is root 3 over 2, is root 3. And consequently, so arctan of root 3 is pi over 3. Well, Shamir now is suggesting 4 pi over 3 as well, right? Because you know, and so is Sean, and I mean, you know that tangent is periodic of period pi. So really, shouldn't this be pi over 3 plus or minus any multiple of pi? And the answer is no. No. No, because the inverse tangent function is a function. So it doesn't spit back infinitely many answers. As Michael suggested, you're restricting the attention to a specific interval, right? For tangent, you are restricting your attention to the interval negative pi over 2 to pi over 2. We must restrict the attention of the tangent function to an interval where it is 1 to 1. And we have decided collectively to restrict our attention to negative pi over 2 to pi over 2. So the inverse function is only defined, the range of the inverse function is only between negative pi over 2 and pi over 2. Nowhere else. And if you use a calculator and you press on the inverse tangent function, that the answer you get is going to be in here. If you wanted all solutions, that's where you now have to argue that the tangent function is periodic of period pi, and then you get all the other ones from there. How did you get from line 3 to line 4? Well, that's because you know these special triangles. You know sine and cosine of certain angles. Arctan of -1. Same question, right? Here we're looking at arctan of √3, right? So when this is √3, we argue that the angle is pi over 3. Now the question is, when is tangent -1? Tangent is -1 at? Joanna, 3 pi over 4, but we're restricting our attention to negative pi over 2 to pi over 2. You've given me something that is outside of this angle. Fix it. Negative pi over 4, there it is. Sine of pi over 4 is -1 over √2. Cosine of negative pi over 4 is 1 over √2. So tangent of negative pi over 4 is -1. Exactly that. Same question. Well, I mean, different function, but same idea. Can we always assume to be in the negative pi over 2 to pi over 2 when we see arctan? Yes, exactly that. Right? Again, it's the same idea, right? We don't know what that is. Let's call that theta. And this is equivalent to asking, if you take sine of both sides, this is equivalent to asking, when is sine of theta -1 over √2? Well, I think we had just argued negative pi over 4. So it's really the same answer as before. Inverse cos of √3 over 2, right? Again, this is equivalent to asking, when is cosine equal to √3 over 2? Ryan is asking, couldn't it also be -3 pi over 4? Again, no. It could have been maybe that for this. But you know that since you're dealing with the arcsine function, this really means that you were dealing with the sine function on an interval which was -1 to 1. And the convention is that you were restricting your attention to this interval. So the answer had better lie in here. Right? Again, with the cosine, you know what interval you're restricting your attention to. The interval is 0 to pi. So the answer it's in the 8th edition of Stewart. Yeah, I want to say the last section in chapter 1. And as people are pointing out, this occurs at pi over 6. The theta is pi over 6. The inverse cosine of √3/2 is pi over 6. Hayden is asking why this specific interval. Is it just convention? Yes. Yes, it is. Everybody agrees that the inverse cosine function is the inverse to the cosine function on the interval 0 to pi. It could not have been 5 pi over 6. Cosine of 5 pi over 6 would be negative. It wouldn't have a, yes, right. Maria, I'm not sure what you're suggesting there. Maybe you meant negative pi over 6, Maria. But again, negative pi over 6 would have been on this side, outside of the domain. And Sean, same answer to you. 11 pi over 6 would be right here, very close to 2 pi, outside of the domain. We are restricting our attention to the interval 0 to pi, otherwise the function would not be 1 to 1. So the inverse cosine function spits out values in this region, 0 to pi. What is the restriction? 0 to pi. Is there any situation where you would change the restriction? Yes. Do you need to state the restriction? No. If you did pi to 2 pi instead, well, exactly. But here's the thing. If you do pi to 2 pi, right? Because, I mean, JD is bringing up the interesting question, right? Right, let's address JD's question here because that is an important one. In the work we did on Wednesday, we restricted our attention of the cosine function to the interval 0 to pi, because it's easily seen to be 1 to 1, and consequently it has an inverse, and we gave it a name. We called it the inverse cosine function or the arc cosine function. This is only valid on the interval 0 to pi. JD is suggesting, what if you restricted your attention to the interval pi to 2 pi? Still 1 to 1, so it still has an inverse. Right? This on the interval pi to 2 pi is 1 to 1, so it has an inverse. Fine. It has an inverse. We're going to give it a name, not the same name as we did over there, because that name's already taken. So if f of x is cosine x, give it a name. It has an inverse, right, because it's 1 to 1, so we give it a name. I mean, I don't know that there's a convention. I don't know that people have given it an actual name, but let's give it a name. Let's call it AC. As in arc cos. It's not the arc cosine function, right? It's just an inverse function. It's just a function that exists. And we know how this works, right? You know that in this case, if you plug in pi into this, you get -1. So the AC function is a function so that if you plug -1 in, you get pi back. If you plug in, this is what, 3 pi over 2? If you plug in 3 pi over 2, you get 0. The AC function is a function so that if you plug 0 in, you get 3 pi over 2 back. You see that it differs from the arc cosine function, because here, arc cos of 0 is pi over 2, not 3 pi over 2. They are different functions. How are we doing? Did we work this out here? Guillaume is asking, in an exam, what if you restricted your attention to a different interval? It's usually going to be very clear what interval you want to be working with. Here, pi over 4, and we're done, right? That was actually not the question. I had just written it down wrong. Sorry about that. It's actually arc sine of sine 5 pi over 4. Sorry about that. And what is that answer? Sorry, what, do we have an answer? Nobody? Right, Youssef is suggesting 5 pi over 4, Kelly pi over 4. And Joanna has given us the right answer of negative pi over 4. Absolutely. Right, again, remember, with the arc sine, It's understood that you are restricting your attention to the interval negative pi over 2 to pi over 2. So whatever answer you spit out, it better be in this interval. Sine of 5 pi over 4 is negative 1 over root 2, which occurs right here when x is negative pi over 4. So negative pi over 4 is the answer. Again, if you take out a calculator and you do sine of 5 pi over 4 and then you do arc sine, this is what you're going to get. Can we just do pi minus 5 pi over 4 to find the answer? Well, I mean, let's not do that. All right. Let's get rid of this 2. How are we going to do that? You may recall that sine squared, right, we have the half angle or double angle identities, 1/2, 1 minus cosine 2x. So if you multiply the whole thing by 2, 2 sine squared is 1 minus cos 2x. And if you interchange, you see that cos 2x is 1 minus 2 sine squared. So cos 2x right, cos 2x is equal to 1 minus 2 sine squared of this business or let me rewrite sine squared this way. And now sine of sine inverse you see what's happening? Sine of sine inverse, these things cancel out, leave you with the 5 over 13. So this is 1 minus 2, 5 over 13 squared. And we're done. Well, let's leave it aside. I mean, it would be nice to find a common denominator and rewrite it as one single fraction. But, I mean, apart from that, there it is. 119 over 169. Thank you. How did the sine functions cancel? Somebody want to address that? If f of x is sine x, f inverse is arc sine x, and you know that the composition of a function and its inverse gives you x. So f of f inverse is equal to x, but that is exactly sine of sine inverse. So the composition, thank you, Kayla. Composition and Willem. Composition of a function and its inverse gives you x. We are asked to simplify this expression. What about the 2? We use this identity here to get rid of that 2. Isabel is suggesting secant, maybe. Let's see. Let's start with inverse sine of x. We don't know what that is. So let's call it theta. This is equivalent to asking for what value of theta is sine theta equal to x. Right? And here, what do I want to do? I want to evaluate tangent of theta. I'm calling arc sine x theta. So I'm really evaluating tangent of theta here. And I'm evaluating tangent of theta for sine of theta equal to x. So let's draw a right angle triangle where the sine of this angle is x, but sine is opposite over hypotenuse. So x over 1. Pythagorean theorem to work out the remaining sine. You know what that is. A squared plus b squared equals c squared. And so it's easy to see that a squared is 1 minus x squared. And so a is the square root of that. And so tangent of this is opposite over adjacent. And there it is. Can the tangent be a hole? I'm not sure what you mean there. Kamal is asking about the 2 in front of the sine squared. Did I forget it? It's there. It's there, and it's still there. Is there an issue there? Why is the exponent on the x not canceled out with the square root? Here, you want to take the square root of each part, but you know that's not how this works, right? Because of the 1 minus, exactly. The square root of a minus b is not the square root of a minus the square root of b. The square root of the whole thing, as Michael suggests. Questions? Let's try one more of these. They're interesting and they actually become important. Yeah, absolutely. You should, I mean, we did that last time, right? Proving trig equations. And why could you not turn tan into sine over cos? That's fine. That's fine. You could have turned tangent here to sine over cos. You already have the sine. So if you wanted to work out the cosine, you could do that. And you get this, and absolutely, yep. Fine. But then you'd still have cosine of inverse sine, which you'd have to work out in exactly the same fashion. Yeah, Isabel. You'll recall again, sine of 2x is 2 sine x cos x, an important identity we saw last time. Let's address this because there's seemingly some confusion here. Some people were suggesting, couldn't you turn this into sine theta over cosine theta? Nothing wrong with that. And wouldn't you know it, sine of theta is x. So you still have x over cosine theta. And theta is arc sine x. So you still have x over cosine of arc sine x. Right? You still have to work this out. I mean, you cannot leave the answer as this. You don't want x's and thetas. You want everything in terms of x. So you'd have to figure out what cosine of theta is, but with the same triangle, cosine is opposite over hypotenuse, which is still x over square root of 1 minus x squared. So however you want to look at it, still the same thing. Convinced? Sine of 2x is 2 sine x cos x, so let's apply it to this, and you get sine of 2x is 2 sine x cos x. Now, cosine of arc cos, this is once again the composition of a function and its inverse. So this is going to give you x. Here, however, sine of arc cos, I mean, it's very similar to this, right? Let's work it out. Well, first let me say that this gives you x, so 2x sine of arc cos. And let's work this out. We don't know what that is, so let's give it a name. Arc cos, let's call it theta, and this is equivalent to cosine of theta equal to x. Let's draw a right angle triangle. And if cosine of theta is equal to x, cosine is adjacent over hypotenuse, x over 1. Pythagorean theorem will again give you this as the square root of 1 minus x squared. So we are really asking, what is sine of theta? And sine is adjacent. Sine is opposite over hypotenuse. So this is 2x square root of 1 minus x squared. No, that's exactly how it's spelled, Victoria, theta. When do you plug in the theta to solve? Well, I mean, I like to give this a name to understand what we're actually looking for, because then this whole thing becomes sine of theta. And then it's easy to see. How do we go from the third line, 1, 2, 3, 3 to 4? This is the composition of a function and its inverse. So this just gives you x, which I have conveniently written out front. How did that come? What does that mean? There it is. Questions? We all right with this? Practice this over the weekend. We'll address concerns, if any, on Monday. What happened to 2x sine? The 2x is there, and then we saw the sine is equal to that. Where do we find answers to book problems? The answers to the odd questions are in the back. That's why I'm suggesting you do the odd questions. We do the even ones in class. These don't have answers, but the odd questions do have answers. Some of you may have bought a solutions manual. Please stay away from that. Do the question, look at the answer in the back. If the answer is right, you're probably fine. And you move on to the next question. If it's wrong, you try it again. If it's still wrong, move on to another question, do a few other questions, get your confidence up, and come back to that question you keep getting wrong. Let me change this x to a y. Jacob wasn't understanding how we were using line 2 to get line 3. This is the y. So sine of 2y is 2 sine y cos y. Sine of 2y is 2 sine y cos y. Are there answers for the appendix problem? I assume there are. I haven't actually checked, but I assume that they're in the back as well. All right, moving on. This is the end of the review material. Now we're moving on to the real calculus material. And what is calculus? Well, you may remember from high school, given a circle, you defined what it meant for a line to be tangent to the circle. A line is tangent to the circle if it touches the circle just at one point. What calculus wants to do is to generalize this idea to curves. So suppose you have a curve. Suppose you have a function. What we want to do is generalize this idea of tangent line and define a line that touches the curve just at one point locally. And we're going to call that a tangent line. That's all Cal 1 is interested in, this tangent line. Well, let's investigate how we're going to do that. Suppose you have this function, y equals f of x. Fix a point A, and we are looking for the tangent line at the point A. A line which locally, right, I mean, if you think of this curve as being a circle, right, very locally, just at that point, it's that same tangent idea that is imported from circles. So what are we going to do? Well, let's take another point, a plus h. Take some value h, of some positive value, say, and look, right? So first of all, we have this point, which is the point a, f of a. And look, consider some value h, and look at f, look at the point on the function, right? This is going to be the point a plus h, f of a plus h. And consider the line joining those 2 points. This is going to be an approximation to the tangent line, an approximation to the line we want. I know what you're thinking. It's a terrible approximation, but let's go with it. We're looking for the tangent line, but of course you understand that all you really need is the slope of the line, because we know the line goes through this point. So you're really, as long as you have the slope, you're good to go. All we want is the slope. Well, let's ask the question, what is the slope of this line? This approximation to the tangent line. Well, that line, what is the slope? You know the slope is the change in y divided by the change in x. How does the y vary? Well, it's f of a plus h minus f of a. And what about the change in x? It's a plus h minus a. Or, if you will, f of a plus h minus f of a over h. This is the slope of this line, which is seen as an approximation to the tangent line that we want. Now, again, let's go back to the fact that it's a terrible approximation, but observe what happens if h gets smaller and smaller. If h gets smaller and smaller, you get a better and better approximation. And so the question becomes, what is the behavior of this expression as h gets closer and closer to 0? That's the question we want to address. What is happening to this expression, to this slope of this approximation, as h gets closer and closer to 0? Because you see what's happening. As h gets closer and closer to 0, we get a better and better approximation to the tangent. Are we back? It's back. How are there only 72 people today? 70. Where's everybody going? Are people being disconnected? Or of the 65? Jesus Christ, what's going on? All right. So how does this behave as h gets closer and closer to 0? Well, now we're back to 97. No, I don't know what's going on. $100. So we give this behavior a name. And call it the limit. Yeah, back up to 124. Right, so we give this behavior a name, and we call it the limit. And this is what we start off by studying. We're going to study the limit process. The limit is the behavior of the function. Let's make it precise with a definition. We say the limit as x goes to a of f of x is L if f of x can be made arbitrarily close to L by taking x sufficiently close to A. This is the definition of a limit. Let's take an example. What is the limit as x goes to 3 of 2x plus 1? Let's take a moment to graph this. We'll get an understanding of the limit process from the graph. Right? You know what the graph of this looks like. It's just a straight line. And what are we looking at? We are looking at the behavior as x gets closer and closer to 3. So what is happening to this function as x, right? If you take values of x very close to 3, if you take values of x very close to 3, this function gets mapped to numbers very close to, as Joanna suggests, very close to 7, right? I mean, this function is very well behaved. If you take any values very close to 3, this is going to be close to 6 plus 1 is going to be close to 7. And consequently, we say that the limit is sufficiently close to A, but not equal to A. Forgot this part in the definition of the limit. Sorry about that. Please make the necessary change. But there it is, right? Limit as x goes to 3 of this function is 7. I mean, you know exactly what's going on here. Let's ask the follow-up question. How does this function behave near -1? If you take values close to -1, what are you close to? What is the behavior of this function? Right? If you take values very close to -1, these get mapped to numbers very close to -1. Thank you, Sean. Right? So the limit is just the behavior. Can we take it a step further here, right? I mean, I think you've understood the behavior as x goes to 3, the behavior as x goes to -1. What if you took a value a in general? Can you tell me the behavior as x goes to, as x approaches that value a? If you take numbers very close to a, your function is going to be very close to, right? This is the function where, right, very close to 3. You had something very close to 7. Close to -1 gave you values close to -1 in a in general. If you take values close to a, this expression is going to be close to 2a plus 1. Absolutely. Right? In the case that a was 3, we had 7. In the case a was -1, we had -1, and so on, and so on. There it is. We have the graph. Very well behaved. We're good to go. Let's take another example. Consider the function x squared. You know the graph of this function. My question to you is, what is the limit as x goes to 3? If you restrict your attention to values very close to 3, the function is going to be very close to very close to 9. Absolutely. If you take values close to -1, values close to -1 get mapped, right? What is the limit as x goes to -1? Values close to -1 get mapped to values that are close to +1. If you're not convinced, take your calculator. Take a number close to 3, 3.01, and square it. See what happens. You're going to get a value very close to 9. Take a number close to 3 but less than 3, 2.998. Square it. See what happens. Right? The limit is the behavior of the function. What is happening to the function? Same thing for values close to -1. Can we generalize? If you took a value a, points close to a, what is the behavior of the function x squared as x goes to a? Values near a get mapped to values close to a squared, thank you. And so on, right? I mean, this is a nice generalization of these two examples here. Let's take an example. you can, somebody's asking where do we do the homework from this weekend. You can finish up Appendix D if you haven't done so already. You can finish up Chapter 1 as well. And here we're starting Chapter 2. So you'll be able to do stuff from 2.1. Not all of it, but some stuff. Suppose that this is the function f of x. Here's my question to you. What is the behavior of that function as x gets closer and closer to 0? Right, 0 is right here. And if you're taking values close to 0, these get mapped to values close to 2. Exactly that. Right? I mean, you have the graph. It's very easy to read off the behavior. What is the limit as x goes to 1? How does this function behave as x approaches 1? Well, 1 is right here. And if you're taking values very close to 1, these values are very close to 0. What about the behavior of the function as x gets closer and closer to 3? Can we describe what happens as x gets closer and closer to 3? And you see the issue, right? You see what's happening. If you take values close to 3, the behavior actually depends, right? If the values are less than 3, then these get mapped to numbers that are close to 2. But if the values are bigger than 3, then these get mapped to values that are close to 3. So there isn't a unique value here. This is not a unique value. The behavior isn't going towards one value, and consequently, we say that this limit does not exist. The behavior cannot be described in a single value. But this, however, brings up the interesting idea of left and right-handed limits. If you were restricting your attention to values less than or equal to 3, then the limit would actually exist and be 2. If you were restricting your attention to values strictly bigger than 3, then the limit would exist as well and be 3. Now, the only way to get to the number 3 is either from numbers less than 3 or from numbers bigger than 3. Those are the only two ways to approach 3. So we introduce the idea of left and right-handed limits and introduce notation while we're at it. Definition, the limit as x goes to a from the left right from the left or from numbers less than a is equal to L, let's just readjust the definition we had for the usual limit. If f of x can be made arbitrarily close to L by taking x sufficiently close to A, but less than A. Similarly, let's introduce the idea of right-handed limit. Similarly, we say the limit as x goes to A from the right of f of x is L if f of x can be made arbitrarily close to L by taking x sufficiently close, to A, but bigger. As x goes to A with a plus here, as opposed to A with a minus, to distinguish between the left-handed limit and the right-handed limit. And if we go back to the example we had before, we can now discuss the limit as x goes to 3 from the left. So if you take values very close to 3 but less, what is the behavior of the function? These values get mapped to stuff in here, very close to. Very close to 2. I'm sure you know that, right? And it's clear from the graph. Similarly, if you look at the limit as x goes to 3 from the right, we are getting closer and closer to 3, but from numbers bigger than 3, what is happening? These numbers in here get mapped to here, very close to 3. What about the limit? What about the limit as x goes to 0 from the left? What is happening? if you are getting closer and closer to 0, but from numbers less than 0, function is getting closer and closer to 2. What about limit as x goes to 0 from the right? Still 2, right? You are taking numbers very close to 0 but bigger than 0. These are getting mapped somewhere here, very close to 2 as well. So the behavior is 2. Let's take a step back now. Before, we were just talking about limit as x goes to 0. And we had discovered independently, right? Whether you're taking them positive or bigger than 0 or less than 0, they're always getting mapped to something close to 2. Now that we have split this idea up into left and right-handed limits, we see that everything agrees here. As opposed to the limit as x goes to 3, which did not have a unique behavior, so the limit itself did not exist. We see that the limit from the left and the limit from the right are actually different, which leads us to the following definition, the following theorem, and we'll end with that. Not really surprising, but since we have now defined left and right-handed limits, we're going to say that, well, theorem, the limit as x goes to a of f of x exists and is L if and only if both left and right-handed limits exist and are L themselves. Think about that for a moment. Well, I'll give you a minute to write it down, and then maybe another minute to think about it. What's there to think about? This is the behavior of the function. L is the behavior of the function as x gets closer and closer to a. There are only 2 ways to get to a, either from the left or from the right. So if the behavior is L, regardless, as long as you're close to a, regardless of whether it's left or it's right, then both left and right-handed limits better be equal to L. Conversely, if both left and right-handed limits exist and are equal to L, then how does the function behave? I'm just using L as a number here, right? In this case, L would have been 2. L as in limit, but it's really just a number. Conversely, if the limit from the left is L and the limit from the right is L, then the limit itself, if you take any number close to A, it's either going to be less than A or bigger than A. But this is the behavior for values less, and this is the behavior for values larger than A. So if both of these exist in our L, the limit itself will exist. We did not get to any questions, but if you want to do some exercises, have a look at page 92, which is really, I want to say section 2.1. I'm not 100% sure on that, but it's limits. So wherever they do limits, page 92 from the 9th edition. Questions here? Anyone? How are we doing? Very good. So thank you all for coming. You guys have a good weekend. 8th edition is page 83. Probably very good. So not too far off. Thank you all for coming. You guys have a good weekend, and I will see you on Monday.